Assalamu alaikum students. We were doing the equilibrium chapter before winter vacations, so we'll continue from where we left last time. We were basically calculating the pH of the weak acid, and we had covered this numerical form for the calculation of the pH of the weak acid. And after that, we also calculated the buffer solution, and I have covered this portion where we were discussing what buffer solution is, how it acts to control the pH of the solution whenever we add any outside acid or a base. So we covered through these equations. We did the basic buffer and the acidic buffer, and also calculated the pH of the buffer solution using this formula. This formula indicates that pH is equal to pKa plus log of anion divided by acid, or in other words, you can also use this formula that Ha is equal to Ka into acid over salt. After that, we had did some portions of these numericals for the buffer solution. So we covered these questions as well. Now our next topic is based upon the solubility product. This is our new topic to start with, solubility product. The solubility product states that whenever we have a sparingly soluble compound, a type of a compound which is not completely dissolved in solution, then for such solutions or substances, we can use the solubility product. It is kind of a constant to find the solubility. So a kind of equilibrium is established when we have a sparingly soluble solid. This kind of equilibrium is given here in the form of an example. You can see that this silver chloride is considered as a sparingly soluble compound. When it dissolves in water, it converts into the silver ions and the chloride ions. So we can apply the equilibrium expression on this type of the reaction. When we do, we have this type of the expression Kc is equal to the concentration of the silver ions, chloride ions divided by the AgCl. Basically, there is some sort of mistake here. It is the mistake is in the book. We have to write Cl negative ion here in the numerator in the aqueous form, and in the denominator it should be AgCl as its concentration. So this is the right formula of the equilibrium expression. This kind of the expression is heterogeneous, as you can see that the reactant is in the solid form, whereas the product are in the aqueous form. That's why we say that they are in the two different physical states or different phases. So these are in the different physical states or different phases. When solids are involved in equilibrium reaction, we simply omit them from the expression. So solids will not be mentioned in case of the equilibrium expression. So to remove that solid form, we can simply multiply this expression with a Kc. AgCl in the solid form will be multiplied by Kc. And as a result of this, we get a new expression that is called Ksp. So Ksp will then be equal to concentration of the Ag ions multiplied by the concentration of the chloride ions. That is what done here. Ksp is equal to Ag ions concentration times chloride ions concentration. For this case, the units of the K will become square of the mole per dm cube. So that's why we have mole square into dm minus 6. The smaller the solubility product, the lower the solubility of the solute. We know that this is a sparingly soluble compound. So if we have smaller value of KSP, which means it indicates that these are present in lesser amount, which means they are less produced in the solution. We cannot use the solubility product KSP for soluble ionic compounds, for example, sodium chloride. The reason is that the interaction between the high concentration of the ions will in solution will interfere with the equilibrium. So KSP is not used for soluble compounds. It is only used for the sparingly soluble. Now from the other source book, you can find this representation of this soluble compound. You can see that an equilibrium is established when undissolved ionic compound is in contact with a saturated solution of its ions. Undissolved, these are the undissolved and these are the dissolved. There is a kind of equilibrium. Some ions are dissolving and some ions are becoming undissolved. So the ions move from the solid to the saturated solution at the same rate as they move from the solution to the solid. So there's there is a rate of ions being dissolved, like moving upward is ions being dissolved and moving downward is ions converting into the solid form. And here it is indication. It is in the aqueous form, which means the ions are dissolved, and it is the solid form, which means undissolved. When solid silver chloride dissolves, it is in contact with the saturated silver chloride solution, and the following equilibrium is set up. So this equilibrium is established when there is different change in the phase. We have this equation from the previous case, and we can simply write the KSP for this kind. KSP is called a solubility product. The name of KSP is solubility product. And these values are quoted at 298 Kelvin. There is another example, Fe2S3. Fe2S3 is another kind of a solid for which the solubility is very less. We call it as sparingly soluble. When it is dissolved in water, you can write the balanced equation. We must have two ions for the I3 plus, and we must have three times of the three times of the 3s negative. So basically, this is the equilibrium for the sparingly soluble compound. So here's the KSP. The idea of solubility product only applies to the ionic compounds that are slightly soluble. Slightly soluble means sparingly soluble. It also stands for sparingly soluble instead of slightly soluble. And the units of solubility product depends upon the type of the ions present in a solution. Since they are square of the iron 3 ions and cube of the S2 minus ion, we need to find the units of this KSP if we are required. Then we have another resource book for the same case. So over here, the same example has been taken, so I do not need to go through this again. So I will move next to the solubility product calculations. The solubility product calculation means we have to find the value of KSP or the value of the concentrations of the ions. So both we will go through different examples which will cover these 2 points, the calculation of KSP and the calculation of the concentration of ions. You may be asked to calculate the solubility product of a compound, which means calculation of KSP from its solubility. This solubility means concentration in terms of mole per dm cube, or You may be asked to calculate the solubility of a compound from its solubility product. So there can be two ways, either calculating KSP or using KSP to find the solubility. An example of each of these types of calculations is shown in the work example 7 and 8. So let's go through the example 8. The example 7 says calculating solubility product from solubility, which means you are supposed to find the value of KSP here. Here we have the question, a saturated solution of magnesium fluoride MgF2 has a solubility of 1.22 into 10 to the minus 3 mole per dm cube. Calculate solubility product of the magnesium fluoride. So we have this compound as a sparingly soluble compound. First we need to dissociate this into ions. So this is given in this equation. MgF2 in the solid form is dissociated into magnesium 2 plus ion plus 2 fluoride ions. After that, we have to use the information given. It says that the solubility is of 1.22 into 10 to the minus 3. That is for one ion, either magnesium ion or the fluoride ions. So here we say that when this amount of the magnesium fluoride is dissolved, when 1.22 amount of this dissolved in 1 dm cube solution, then the concentration of Mg2 plus ion will be equal to this much, since we can see there is one ratio 1. 1 mole of MgF2 produces 1 mole of magnesium ions. So there will be equal amounts, since it is sparingly soluble. When it is sparingly soluble, it means we can have equal amounts here. And then we can also take the ratio between fluoride ions and MgF2. So the concentration of fluoride ions will become 2 times of the amount of the 1.22. So this is the value for fluoride ions. So after that, we have to simply use this formula KSP is equal to, okay, convert this equation into the KSP form as well. We are supposed to convert it into KSP formula. KSP will become concentration of the magnesium ions, as we have been doing, into concentration of the fluoride ions. But here the fluoride ions are present by 2 moles, which means this coefficient 2 will become power over here. So fluoride ions will have power 2. After that, we will substitute the values. For magnesium, we have the same value, but for fluoride ion, we have basically multiplied as it was done here. We had to multiply the concentration of fluoride with 2. But same value is also squared. So it is also squared. So what do you see here? I can write in the simple words that if initially MgF2 was converting into let's suppose X for magnesium and 2 times for fluoride. These are basically the solubility in terms of concentrations. And when we were applying the KSP, we said that it is basically X, concentration of X into the 2X will become squared, since 2 is also needs to be converted into the power. So you can have X times 4S square, 4X square, or you can have 4X cube. For any compound in which one ion has only 1 mole but the other ion has 2 moles, like in this case, we got from here 2 times of fluoride ions, you will always get this type of the expression. And over here, X will be equal to the amount which is basically taken. We took this we took this amount of the amount of the MgF2. We had this solubility of the magnesium or the fluoride. Anyways, so substituting the values, you get this answer. Now after that, we have to find the units. So the unit will become unit of Mg into units of F negative. The F negative basically is squared, which means it would become mole per dm cube with square, and its power is 1. So multiplying these two, you will get this as a final unit, mole cube dm minus 9. And you can clearly see here this x is cube and it is solubility in terms of mole per dm cube. So mole per dm cube with power 3 will give you mole 3 and dm minus 9, and it is similarly here. So that's what I said, that whenever we have such type of the ionic compound, then you will get this type of the expression, and this x is basically the solubility in terms of its value. Let's move to the next question. Calculate the solubility of the lead to chloride if 25 cm cube saturated solution contains 0.11035 gram dissolved in it. Okay, here we have lead chloride as a solubility salt, as a sparingly soluble salt, but uh, we have to calculate the solubility, which means we must be given the we have to find the solubility here. It is again same question like before. We have to find the KSV. If 25 cm cube saturated solution contains 0. Over here we are given the value in terms of volume and gram, which is a mass. So we have to take into account this volume and mass, which means we have to convert them into the mole per dm cube. How can we do it? We have to convert this mass into the moles. So basically, the MR of this lead to chloride must be calculated. The MR of this lead chloride is equal to 278.2. You can use the periodic table for this purpose. The mass is already given. And what else we have here? We have to find the mass in terms of the decimeter cube. Like, you know that we had this much volume. We have to convert this volume into the dm cube. How is it converted into the dm cube? By, 25 divided by 1000 will give you 0.025 dm cube. We can take the relationship of the volume and the mass. We can say that 0.11035 gram was dissolved in 25 cm cube. Then how much mass will be dissolved in 1 dm cube, which means in 1000 cm cube, how much mass will be dissolved? This will become x. So it means 0.11 times 1000 will be equal to 25x. So you get this type of the relation. From here you have got the amount of the lead to chloride in dm cube instead of the 25 cm cube. So this is mass in dm cube. Now you can find easily the moles from here. So mass divided by molar mass gives the mole. So this is the mole of the lead to chloride. So basically what we have done, we have converted the mass in gram and volume of 25 cm cube into the mole per dm cube. Okay, this is done. After that, we construct the equation for the solubility of the lead to chloride. We have this relation: 1 mole of lead ion is there and 2 moles of the chloride ions are there. After that, we know that the if this amount is dissolved, it will produce 1 mole of this, but 2 moles of the chloride ions, since there are 2 moles present here. So two times moles of that will be produced. Now you will substitute these values into the expression of KSP. This is the expression of KSP. So lead will be the same value, but for chloride ions, it will be 2 times of that value. So you substitute the value here. After that, you have to take the scale as well. So scale is taken here. Since chloride ions must be in the scale form. Okay, then you will use a calculator, you will calculate the value and you get the answer. Again, you can see the units are the same, mole cube and dm minus 9. It is why? Because we have 2x square, 2x whole square times x. The same thing which I told you before. And as a result of this, you get 4x cube. And x is present in mole per dm cube. There is another question here. Calculate the solubility of strontium sulfate, which is pattern soluble compound, for which KSP is given. So KSP is given, you have to calculate the solubility. First of all, you will write the equilibrium reaction, which is not given here. So strontium sulfate will convert into the strontium plus 2 and sulfate minus 2. So 1:1. Both ions are present by 1:1, which means we can simply derive the equation, and KSP is equal to this much. We do not know the solubility here. So for solubility, we can consider it as x and this one also x. We do not know the values of x. Now in the expression, I can write KSP is equal to x square. KSP value is given. So I will take the square root of this value. So that's why it is taking the square root. So the square root of this KSP will give me the value of x, that is 7.1. And that is the solubility of the any of these two ions, either strontium ions or the sulfate ions. There's another example. The solubility of calcium hydroxide is 1.5 into 10 to the minus 2 mole per dm cube, but here 1 mole of calcium hydroxide dissolves to give 1 mole of calcium ions and 2 moles of hydroxide ions. Okay, we have the solubility of calcium hydroxide this much, but as a result of this solubility, we will get this kind of equation: Ca2 plus and 2 times of the hydroxide ions, and this is the value for one solubility, which means we have to calculate the KSP here. The KSP will become concentration of Ca as x and 2 times of the concentration of hydroxide ions, but this will also be converted into the scale. So KSP will become x times 2x with power 2. So that is what done here. They then substitute the value of the x, which is 4.5 or 1.5 into 10 to the minus 2, and then calculated the KSP. So that is how these questions are done. We will keep practicing these questions in our next class. Till then, take care and Allah Hafiz.